In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about electromagnetic acoustic transducer. An electromagnetic acoustic transducer is a transducer for non-contact acoustic wave generation and reception in conducting materials. Its effect is based on electromagnetic mechanisms which don't need direct coupling with the surface of the material. Due to this couplant-free feature, electromagnetic acoustic transducers are particularly useful in harsh, for example, hot, cold, clean, or dry environment. Electromagnetic acoustic transducers are suitable to generate all kinds of waves in metallic and or magnetostrictive materials depending on the design and orientation of coils and magnets. Shear horizontal bulk wave mode, norm beam or angle beam, surface wave, plate waves such as SH and lamp wave, and all sorts of other bulk and guided wave modes can be excited. After decades of research and development, electromagnetic acoustic transducer has found its applications in many industries such as primary metal manufacturing and processing, automotive, railroad, pipeline, boiler, and pressure vessel industries, in which they are typically used for non-destructive testing of metallic structures. Basic components. There are two basic components in an electromagnetic acoustic transducer. One is a magnet and the other is an electric coil. The magnet can be a permanent magnet or an electromagnet, which produces a static or a quasi-static magnetic field. In a electromagnetic acoustic transducer terminology, this field is called bias magnetic field. The electric coil is driven with an alternating current electric signal and ultrasonic frequency, typically in the range from 20 kHz to 10 MHz based on the application needs. The signal can be a continuous wave, a spike pulse, or tone burst signal. The electric coil with alternating current also generates an AC magnet field. When the test material is close to the electromagnetic acoustic transducer, ultrasonic waves are generated in the test material through the interaction of the two magnetic fields. Transduction mechanism. There are two mechanisms to generate waves through magnetic field interaction. One is Lorentz force when the material is conductive. The other is magnetostriction when the material is ferromagnetic. The chapter of Lorentz force. The AC current in the electric coil generates eddy current on the surface of the material. According to the theory of electromagnetic induction, the distribution of eddy current is only at a very thin layer of the material called skin depth. This depth reduces with the increase of AC frequency, the material conductivity and permeability. Typically for 1 MHz AC excitation, the skin depth is only a fraction of millimeter for primary metals like steel, copper, and aluminum. The eddy current in the magnetic field experiences Lorentz force. In a microscopic view, the Lorentz force is applied on the electrons in the eddy current. In a macroscopic view, the Lorentz force is applied on the surface region of the material due to the interaction between electrons and atoms. The distribution of Lorentz force is primarily controlled by the design of magnet and design of the electric coil, and is affected by the properties of the test material, the relative position between the transducer and the test bar, and the excitation signal for the transducer. The special distribution of Lorentz force determines the precise nature of the elastic disturbances and how they propagate from the source. A majority of successful electromagnetic acoustic transducer applications are based on the Lorentz force mechanism. The chapter of magnetostriction. A ferromagnetic material will have a dimensional change when an external magnetic field is applied. This effect is called magnetostriction. The flux field of a magnet expands or collapses depending on the arrangement of ferromagnetic material having inducing voltage in a coil, and the amount of change is affected by the magnitude and direction of the field. The AC current in the electric coil induces an AC magnetic field and thus produces magnetostriction at an ultrasonic frequency in the material. The disturbances caused by magnetostriction then propagate in the material as an ultrasound wave. In polycrystalline material, the magnetostriction response is very complicated. It is affected by the direction of the bias field, the direction of the field from the AC electric coil, the strength of the bias field, and the amplitude of the AC current. In some cases, one or two peak response may be observed with the increase of bias field. In some cases, the response can be improved significantly with the change of relative direction between the bias magnetic field and the AC magnetic field. Quantitatively, the magnetostriction may be described in a similar mathematical formats as piezoelectric constants. Empirically, a lot of experience is needed to fully understand the magnetostriction phenomena. The magnetostriction effect has been used to generate both SH-type and LAM-type waves in steel products. Recently, due to a stronger magnetostriction effect in nickel than steel, magnetostriction sensors using nickel patches have been developed for the non-destructive testing of steel products. Comparison with piezoelectric transducers. As an ultrasonic testing method, electromagnetic acoustic transducer has all of the advantages of ultrasonic testing compared to the other NDT methods. Just like piezoelectric UT probes, electromagnetic acoustic transducer probes can be used in pulse, echo, pitched catch, and true transmission configurations. Electromagnetic acoustic transducers probes can also be assembled into phase array probes, delivering focusing and beam steering capabilities. And what are the advantages? Compared to piezoelectric transducers, electromagnetic acoustic transducers probes have the following advantages. The first advantage is no couplant is needed based on the transduction mechanism of electromagnetic acoustic transducers. Couplant is not required. This makes electromagnetic acoustic transducers ideal for inspections at temperatures below the freezing point and above the evaporation point of liquid couplants. It also makes it convenient for situations where couplant handling would be impractical. The second advantage is that electromagnetic acoustic transducers is a non-contact method, although proximity is preferred. A physical contact between the transducer and the specimen under test is not required. The third one is that the dry inspection, since no plant is needed, the electromagnetic acoustic transducer inspection can be performed in a dry environment. The fourth one is less sensitive to surface conduction. With contact-based piezoelectric transducers, the test surface has to be machined smoothly to ensure coupling. Using electromagnetic acoustic transducer, the requirements to surface smoothness are less stringent. The only requirement is to remove loose scale and lag. The fifth advantage is that easier for sensor deployment using piezoelectric transducers. The wave propagation angle in the test part is affected by the Snell's law. As a result, a small variation in sensor deployment may cause a significant change in the refracted angle. The sixth advantage is that easier to generate SH-type waves using piezoelectric transducers. SH wave is difficult to couple to the test part. Electromagnetic acoustic transducers provide a convenient means of generating SH bulk wave and SH guided waves. The challenge and disadvantage. The disadvantage of electromagnetic compared to piezoelectric UT can be summarized as follows. The first one is low transduction efficiency. Electromagnetic transducers typically produce raw signal of lower power than piezoelectric transducers. As a result, more sophisticated signal processing techniques are needed to isolate signal from noise. The second challenge and disadvantage can be limited to metallic and or magnetic products. NDT or plastic and ceramic material is not suitable for or at least not convenient using electromagnetic acoustic transducers. The third disadvantage can be that size constraints. Although there are electromagnetic acoustic transducers as small as a penny, commonly used transducers are large in size. Low profile electromagnetic acoustic transducers problems are still under research and development due to their size constraints. Electromagnetic acoustic transducer phase array is also difficult to be made from very small elements. The fourth one is caution must be taken when handling magnets around steel products. And what are the applications? Electromagnetic acoustic transducers has been used in a broad range of applications and has the potential to be used in many others. A brief and incomplete list is as follows. The first one is thickness measurement for various applications. The second one is fallout detection in steel products. The third application can be plate lamination defect inspection. The fourth one is bonded structure lamination detection. The fifth one is laser weld inspection for automotive components. The sixth one is weld inspection for coil joint tubes and pipes. The seventh applications can be a pipeline service inspection. The eighth applications can be railroad rail and wheel inspection. The ninth one is authentic weld inspection for the power industry. The 10th one is material characterization. In addition to the above mentioned applications, which fall under the category of non-destructive testing, electromagnetic acoustic testing, acoustic transducers have been used in research for ultrasonic communication, where they generated and received an acoustic signal in a metallical structure. Ultrasonic communication is particularly useful in areas where radio frequency cannot be used. This includes underwater and underground environments as well as sealed environments, for example, communication with a sensor inside a pressure tank. The use of electromagnetic transducers, acoustic transducers, is also under study for biomedical applications, in particular for electromagnetic acoustic image. So here there is a parameter section and there are multiple parameters here such as a number of turns in coil, peak driving, voltage, frequency at which loss factor is given, angular frequency at which loss factor is given, maximal steady frequency, speed of sound in air, and minimum wavelength. And the next one is the definition, the variable definition section. And you see the expression and the formula that we want to calculate and compute coil power and also acoustic efficiency in our physical module. There is an integration section with a specific boundary condition and the special and the geometry that we have is two circle based on some rectangle that has the coil. The coil will be uh, located here. And the material we have used is air, soft iron, composite, closed foam, cold glass, and generic ferrite. This is magnetic or ferromagnetic. And the physical module that we have used uh, are three different physical module: magnetic fields, pressure acoustic frequency domain, and solid mechanics. Solid mechanics because we want to measure the acoustic uh, pressure that make a stress and a strain to our geometry. And the next one is uh, pressure acoustic frequency domain and magnetic field because we have a coil and there is a circle here and we have a magnetic material as a generic ferrite, for example. You see that we have used the free space and the geometry that you can see with a specific stabilization. And the equation that you can see, the equation is based on magnetic field stationary and magnetic insulation part, initial values, ampere laws in solids. You see that this ampere come from this small rectangle and soft iron is outside the rectangle, and non-conductive is the wire that is here in the blue wire and the domain code. The next pressure acoustic is that we used azimuthal mode number and port substituting and etc. Exterior field calculation, narrow region acoustic, and here we have a solid mechanics. After all, I want to show that blocked coil inductance and the X horizontal is based on frequency and hertz, and the Y one is based on coil inductance and it's based on the Henry uh, because it's for related to induction. And you see that whenever we increase the frequency, it's much more than the 1000, and you can see the coil inductance will be discharged and the this induction will go to the 0 Henry. And the acoustic pressure, and here you can see uh, as a pellet contour the inductance induced current, and also electromagnetic acoustic transducers which produce ultrasonic waves without any coupling medium in the surface of an electrically conductive material. Here in this simulation, the difference between piezoelectric and electromagnetic generation and reception of ultrasonic waves is described. The next part presents the mechanism is acting mainly during ultrasound excitation by electromagnetic acoustic transducers, the Lorentz force and magnetostrictions, and the next part considers electromagnetic acoustic transducers based on the Lorentz force, and the last one looks at transducers using magnetostrictions. Typical arrangement of radiofrequency coils and magnets are shown here, and directivity patterns are presented. Methods for varying the beam angle are explained. Applications of electromagnetic acoustic transducers are described. So thank you so much for watching my tutorial video until the end. And also you can download this loudspeaker driver Comsol simulation from github.com/masterscript. And today is 12th of February 2026, and the time is 8:46 o'clock in the afternoon that I have recorded this simulation for you.